All right, so let's do homework 3. The first problem is the component manufacturing problem, where you need to decide how many of each component 1, 2, and 3 to produce. So if you look at my question part A, I'm asking determine the number of components 1, 2, and 3 to produce such that the total profit is maximized. Right? So we need to decide how many component 1 to produce, how many component 2 to produce, and how many component 3 to produce, such that the total profit will be maximized. So this means that our decision variables are production quantities for component 1, 2, and 3. So I'm just going to write that down here. Decision variables are production quantities for component 1, 2, and 3. Right? Component 2 and component 3. So we are going to start, again, you can start with any number you want, but we are going to start with some zeros and ones so that I can kind of follow through the calculations in my head. Otherwise, it's just difficult for me. All right, so that's the decision variable. The next part of the model is the objective function. So the objective function here is the total profit, right? Because that's what I wanted to do. I wanted to find out the production quantities such that the total profit is maximized, right? So that is going to be my objective function. I'm going to write total profit. And to calculate total profit, I need to look at this array right here. So right here, I have the profit contribution for component 1, profit contribution for component 2, and profit contribution for component 3, which means that if you are selling, if you're making one component 1, it's going to give you $8. If you're making one component 2, it's going to give you $6. If you're making one component 3, it's going to give you $9. These are your production quantities, and these are your profit contributions per unit, which means that we can use sum product function to calculate the total profit. So it's going to be sum product with my profit array and the decision variable array, which is how many of each component you are producing. So right now I'm only producing one component 2, which is why my profit is just $6. All right, so the third part of the model are constraints. So what are my constraints? I have a few constraints here. So first of all, each component 1, to make each component 1, you need to spend 5 minutes in Shaper. To make each component 2, you need to spend 8 minutes in Shaper. And to make each component 3, you need to make 4 minutes in the Shaper. You need 4 minutes in the Shaper. The total minutes you have is 7 to 200. So this is a resource constraint, which means the total amount of time that you're spending in Shaper that needs to be less than equals to 7 to 200 minutes. So I'm going to name it as Shaper availability constraint. And the constraint is basically going to be the left-hand side of the constraint is going to be whatever total required. I can name it total required. Even if you don't name it, it doesn't matter. As long as you have everything formula-wise, you should be good. And assign and total available. All right. So what is the total required? For example, right now, you're making only one component 2. That means that you need 8 minutes in the Shaper. But if you make also component 1 and component 2, it's going to add 5 minutes per unit and 4 minutes per unit. So we can again use the sum product function to calculate the Shaper time required, which is the Shaper array and then the production quantities array. And this needs to be less than equals to total time available, which is right here, 7,200 minutes. Similarly, we can write down the grinder availability constraint. And the total time you require in grinder is again can be calculated by some product of the grinder array and the production quantities. So this needs to be less than or equals to 6600. All right, so these are my shaper and grinder availability constraints. So now I also have a few constraints in terms of demand. So component one, minimum demand. So according to this parameter spaces, component one needs to be produced at least 600 units. So there is a 600 units of demand for component one already. So we need to produce at least 600 units of component one. So I'm going to write the component one, whatever you're producing, I'm going to link it to production quantities of component one. That needs to be at least, which means greater than equals to 600. It always has to be higher than 600 because you have to meet the demand of 600 for component one. We also have a few max demand functions. So component one max demand. I'm again going to link it to component one production quantity. That needs to be less than equals to right here 1000. Finally, component two. So you see component two does not have a minimum demand requirement, just that it is greater than equals to 0, but it does have a maximum production requirement. Right? So component two has to be however many components to produce, it has to be, the number has to be lower than 1000, right? I'm going to write component two max demand and link it to component two, and that has to be lower than 1000. Finally, component three max demand, that is lower than 200. All right, so now my model is ready. Let's go ahead and solve it. Solver. So my objective function is total profit, maximizing my profit. The decision variables are production quantities. Let's add the constraint. So these two are less than or equals to constraints. So I'm going to add them together. Right here is it greater than or equals to constraints. So I need to add them separately than the other constraints. And then these three constraints are less than or equals to constraint again. And I need to make sure that I produce a non-negative amount of quantities. So I'm going to click here, and the method would be simplex open. There you go. Go ahead and press solve. Solver found a solution. Constraints and optimality condition are satisfied. Keep solver solution. Click OK. And the total profit is 10,850. So I'm going to write here component one, produce optimal production quantities. Component one, 1000. Component two, 175. And component three, 200. Total profit equals to 10,850. Okay, so that's the first portion. Now in part B, I'm asking if one more hour could be made available on the shaper, how much would it be worth? That means that if right now you have 7,200 minutes in the shaper, if I add one more hour, which is 60 minutes. So if I add 60 minutes, this becomes 7260. And how does that changes our total profit? So go ahead and solve the model again. And right now my total profit is $10,895. So my profit increased by So what is my increase in profit? My profit increased by 10,895 minus, it was before 10,850. So $45. So one more hour in the shaper would be worth $45. Okay. All right. So now let's move on to part 2. So part 2 is a transportation or a network optimization model. And you need to figure out how much electricity to send from plant 1 to city 1, plant 1 to city 2, plant 1 to city 3, plant 1 to city 4, plant 2 to city 1, plant 2 to city 2, plant 2 to city 3, plant 2 to city 4, and same for plant 3. So you have 12 decision variables. And the optimal way to figure this out is to find a way that minimizes your total shipment cost. Okay. You have some supply constraints and some demand constraints. So we are going to start with the decision variables. So what we would do, we would just copy and paste this cost matrix right here. And then I'm going to just change the cell styles right here. Yeah, that's good. And I'm going to change these numbers and start with some 0 and 1. So this is exactly where I'm going to write down, our solver is going to give me how much to send from plant 1 to city 1, plant 2 to city 1, and basically all my decision variables. So you're going to start with any random number. It doesn't matter what you start with. But we are going to use these cells as decision variable cells. So I'm going to just put some kind of formatting. All right. So next is objective function. Objective function is going to be total cost. And you can calculate, so these are your shipping costs per unit. So if you send 1 unit from plant 1 to city 1, it's going to cost you $8, right? So if you're sending, let's say right now you're sending 1 unit, it's going to cost you $8. If you send 2 units, it's going to cost you 8 multiplied by 2, which is $16, right? And then, so if you are, so basically what you need to do, you need to product the shipping cost by product, you need to multiply shipping cost by the amount of electricity, in this case, you are sending from plant 1 to city 1, and then sum all of the shipping costs, right? So you have to do, like in this case, you have to do, for example, 8 multiplied by 1 plus 6 multiplied by 1 plus 10 multiplied by 0 plus 9 multiplied by 1 plus 9 multiplied by 0, so on and so forth. So we can do that easily using the sum product. Or the sum product, then all my costs and all my decision variables. Okay. Now let's move to constraints. So in any kind of network optimization problem, you have 2 types of constraints. The first one is supply side constraints. So we have 3 supply sides, plant 1, plant 2, and plant 3. We need to make sure that we are not sending out more than what the supply actually is at each of these plants. So to do that, whatever I'm sending, I'm going to sum up all that you are sending from plant 1, and that needs to be less than equals to whatever is available at plant 1. Similarly for plant 2, whatever you are sending from plant 2 needs to be less than equals to whatever is available to plant 2. Similarly for plant 2, plant 3, the total amount that you are sending out from plant 3 needs to be less than equals to 40. So these are my supply side constraints. Now let's move on to demand side constraints. So demand side constraints are essentially making sure that the demand at each of the cities are satisfied. In other words, whatever you are sending to city 1, the sum should be at least 45. So you need to meet the demand. So you need to send at least 45. So I'm going to again write down city 1, city 2, city 3, and city 4. So how much you're sending to city 1? That needs to be at least whatever the demand for city 1 is. Similarly, this is what you're sending to city 2. That needs to be at least whatever city 2 demand is. Again, the total amount that you're sending to city 3 needs to be at least 30. And the total amount that you're sending to city 4, excuse me, needs to be at least 30. Okay, so now we have everything. Let's solve the problem. My objective function is my total cost. I am minimizing my cost. The variables that you're changing are right here. These are your decision variables. The first constraint are the supply side constraints. And then I have the demand side constraints. So make unconstrained variables non-negative. And I'm going to choose simplex LP as my solving method. Go ahead and solve it. The total cost is 1,020. So I'm just going to write that down. I'm just going to write down that minimum total cost. As long as you're giving me either the values of the objective function or the values of the decision variables, you're good. All right. So part B is identify the binding and non-binding constraints in your solution. So there are many ways you can get it, but you can basically just look at your solution. So if you see that your constraints, the right-hand side of your constraint exactly matches the left-hand side of your constraint, then those constraints are binding. So as you can notice, for all of this, the right-hand side and the left-hand side match exactly. 35, 35, 50, 50, 40, 40, 45, 45, 20, 20, 30, 30, and 30, 30. So I'm going to say that all my constraints are binding. Okay. Part C says, if you had to decide to increase supply at only one of these plants, which one would you choose and why? So essentially, I'm asking if you had to choose among this 1, 2, 3, if you had to choose to increase supply at one of these plants, which one do you think will actually help you lower your cost even further, right? So to get that, we need to get the sensitivity report. So once you solve it, right here, you're going to click sensitivity. So here's your sensitivity report. And the thing that you're going to look at are your shadow prices. So these are your shadow prices for plant 1, 2, and 3 constraints. I'm just going to quickly copy that up and put here. So the shadow price means if you increase one unit of your right-hand side for each of these constraints, then the objective value will change by the shadow price. So for example, if you increase the plant 1 supply by 1 unit, your objective value, the total cost, will go down by 3 units. Whereas if you increase supply at plant 2 and 3, that will not affect the total cost, right? So that means that if I were to increase, I would basically increase plant 1 and not 2 and 3. So I would increase supply at plant 1 because it has the lowest shadow price. Finally, the last question, what happens to your solution if plant 1 can supply 20 mega kilowatt hours of electricity? So right now my plant 1 supply is 35. So I'm asking what happens if plant 1 only can supply 20. So let's do that. Let's change 20 to 35 and let us resolve the model. If you resolve the model, then it basically shows you solver could not find a feasible solution. Solver cannot find a point for which all constraints are satisfied. So there's no way you can actually meet all the demands if plant 1 only has a supply of 20. Okay, so I'm going to click OK, and that is what I'm going to write down here. So no feasible solution. All right, so that's our part 2. Now let's move on to part 3. So part 3 is a problem where you need to figure out which of these items to pick in your small backpack, and the volume of the backpack is 0.8, right? Cubic feet. So everything is in cubic feet, so that's good. So let's read the question A. So I'm asking how should the hiker pack this bag? So these items are available, which item 1 has 0.2 volume cubic feet and 12 grams of protein. Item 2 has 0.5 volume cubic feet and 40 grams of protein, and so on and so forth. In other words, which of item 1, 2, 3, 4, and 5 should the hiker pack in the bag such that the total protein content is maximized? So you are trying to figure out which of these items to pick such that the total protein is maximized. Keep in mind that only one of each item is available. And also, so you cannot basically cut your can, right? So you have to take one of whole item. So this tells you that this is a binary optimization model because only one of each item is available and you cannot cut the item or you cannot divide the item in any way. So let us model the model. Let us first start with decision variables. So your decision variables are basically all of your items and whether to pick them or not. So I'm going to put it here, pick or not. And you can start with any numbers of ones and zeros, where ones means that you do pick them and 0 means that you do not pick them. All right, now next goes your objective function. So your objective function is total protein because that is what you are trying to maximize. And you can calculate the total protein by some product of the grams of protein right here with your decision variable. Next, your constraint. So you only have one constraint here, and the constraint is that your volume of your backpack is 0.8 cubic feet. So I'm gonna write something like volume constraint. So the left-hand side of your constraint is essentially how much I am packing, right? Or how much the hiker is packing. That is some product again of pick or not, decision variables, and volume. And you need to pack it such a way that it fits in your backpack, which is has 0.8 cubic feet volume. So that's basically it. Go ahead and solve the model. Objective function is total protein. You are maximizing a total protein. Variable changing are this. Subject to constraint, volume constraint less than equals to 0.8. And you need to tell Excel that your decision variables are binary. Okay. That's it. Let's solve the model. And YO2, the optimal thing to do would be take one item 2 and one item 4. Total protein equals to 60 grams. Now, part B says, what happens to the solution if the hiker does not want to include item 2 and item 3 for sure? So right now, the hiker is including item 2. So this is not the right solution. To do this part, let's go ahead in the solver again. And now all we need to do, we need to add additional constraints that will tell you that item 2 should be, the decision variable for item 2 should be 0, as well as the decision variable for item 3, add one more. The decision variable for item 3 is also exactly equals to 0. Okay, so that's it. And then go ahead and again solve the model. So in this case, solver is C12 and C13. Right, okay. And wait, sorry, I think I messed it up. So this is this, that's your objective function. Changing variables, all of them. And then I'm just gonna, this is fine, this looks fine, everything looks fine. Okay. So what happens if your hiker does not want to include item 2 or 3? Then the hiker would include, so pick item 1, 4, and 5. Okay, and the total protein equals to 42 grams. Okay, finally, I'm asking what happens to the solution if the hiker decides to include at least one of item 1 and 2. I think they should be probably worded as R. But anyway, what I want to say is that if the hiker wants to pick at least one of item 1 or 2, so the hiker could pick item 1 and not pick item 2, or the hiker could pick item 2 and not pick item 1, or the hiker could pick both item 1 and 2. So to do that, we need to add an extra constraint. I'm gonna name pick item 1 plus 2, or 2, sorry. Pick item, or at least pick item 1 or 2. Okay. So in this case, all you need to make sure is the sum of item 1 and item 2 is at least 1. So if the sum is not at least 1, that means the sum is 0, which means that both item 2 and item 1 has 0 as their decision variable, which is not allowed, right? Because they have to take at least one of item 1 and 2. All right, so that's it. Let's go ahead and solve the model. I'm going to delete this, and then add this extra constraint. Okay, so now we are back to the original model, which says that take one item 2 and one item 4. And the total protein equals to 60 grams. Right? So why did we come back to the original problem? Because in the original problem, you were already taking item 2, right? So you're already taking one of item 1 or 2. So you're taking item 2. That means the original problem we're already satisfying this constraint. That's why we're back to the original problem. So that's all. So that's all the solution parts for homework 3, and hope you have a good exam.